Welcome you all to the lab session. This is going to be the last session on features of FreeRTOS as well as how to use it on ESP32. I'm teaching all this because when you are designing some application, you may have to use some of the features and you need to know at least the bare minimum things which are supported by FreeRTOS on ESP32. And this, whatever you gain knowledge here will be useful for you to develop any application on any other processor using any OS. It doesn't matter whether it is FreeRTOS or QNX or Linux. But this basic knowledge of OS calls and how to use them in embedded systems is very important for you to write any application on, especially for IoT devices. Okay, so let us spend some time on two key important things. Message queues first and then ring buffers. So let me start with message queue. I'm sure you might have studied it in your OS courses in your bachelor's. So let us see now. Suppose process P1 is there and some other process P2. One thing I want to tell you, you might have studied about threads and processes, and threads operate in the context of process and the context switch between threads are easier, all those things, right? When we talk here on FreeRTOS, we are not differentiating between processor and threads here because there is no concept of threads in this system. FreeRTOS here, there are only processes, and whatever I tell you about the processes and the interaction between the processes, they are also valid for threads, but you may have to read the documentation of a particular operating system to know some differences in them. Okay, if it is Linux or some other operating system or real-time operating system, you may have to know a little bit more about whether a feature is supported for a process or is it a thread or for both. But in our case, there are no threads in this case, FreeRTOS, there are only processes. And one most important thing to remember is when you are creating a task here, I think I have mentioned it earlier, we are passing a function pointer, right? That function pointer, if you remember, the prototype of that is void and then some function and void star. Now, why did they give void here? It is not uniform across all operating systems. Remember that. It is not void on Linux. It is not void on Linux. It is not void on POSIX. POSIX, okay, let us not talk about it. Let me talk about Linux, okay. It doesn't have void here. A function pointer which is passed to creating a task is void star on Linux. Okay, it is void star function pointer function and then some parameter. This parameter is always a void star because we don't know what type of parameter is going to come to a function when a thread is created or a process is created. But when that function pointer has a void star as a return, it means that somebody is ready to receive what is being returned by the function. When I say returned by the function, it is not actually a function, it is an entry point to a task. So it is something which is returned by a task is ready to be received by somebody. So let me explain what I mean by that. In Linux, what happens is we have, when we create a process, the init process is there. Okay, that is the first process to be created on Linux, and that will be the parent of all the other tasks which are there in the system. But suppose you have a application task P1 and it creates another process, a child process C1. Now there is a parent-child relationship maintained within the OS in Linux. So when it creates a child thread, the function entry point is a void star and then the function, then some parameter, which is also a void star. Now, what is getting returned by this child thread is normally to be received by the parent. You might have heard about the join pthread join. Okay, join. Pthread join is a function call where a parent can wait for a particular child to be terminated. During that time, whatever the child thread is returning is returned through the void star, and the parent process can receive it, and it can do some process accordingly. It may know that what conditions the child has died, the child thread has terminated. That reasoning can be done by the parent process. Because there is a parent-child relationship in Linux, there is a void star in the entry point for the thread creation. So it can afford to return something and there is somebody to receive it. Now, what if a parent has created a child and the parent has terminated, but the child is still running? In that case, you might have heard about it. Now, this is in a zombie state, and the child thread, if a parent is not there, it can be linked to the OS task, so that there is somebody to take care of the processes in the Linux system. It may be finally be connected to the init task, which is the first task which is created by Linux. So remember this, that in FreeRTOS there is no void star because there are no parent-child relationship in the threads creation. So in FreeRTOS, a process is creating another process. Suppose P1 is creating P2. P2 does not know that it was created by P1. There is no relationship between them. It is just another entity which is there in the system, and they run. Now, what is the problem when you don't have a void star in a function which is creating the task? Now, when this function ends, there is no void star here. There is a void here. So let me maybe rewrite it again. This is the function that you have created, a task. You have entered it with some parameter. Now, when it gets ended, when it gets finished, there is nothing to go back to. That is why you get an exception when you do not kill the process at the end of its function. Either it should get killed, be delete, via task delete, task delete, or it should continue to execute within the for loop or something, while loop, so that it will continue to be alive. But if it is coming to the end of the function, you have to make sure that it is getting deleted. That is very important. Remember that. Now, coming back to message queue. So in FreeRTOS, there are different tasks which are there. And then you know that in ESP32, there are two cores are there, core 0, core 1. Now, what happens is there is a common shared memory. It's completely, all the memory is shared. Okay. The memory which is there in the system is common between core 0 and core 1. That means they see the same address in this core. From this core, the same address is seen by the same location is also seen by the same address. Whatever the address it is seeing, it will be seen by the other core also. That means the process which is running on this core will also see the same location if it is having the address. Now, let us talk about message queue. Message queue is something which is a OS resource, message queue, which is having multiple configurable parameters. How many number of messages which are there? Number of messages that a message queue can hold at a time. And then there will be a wait queue for threads to T1, T2. I am calling thread and process very mixingly because there is no difference between them. So there is a queue for putting the data into the message queue. Queue of threads or processes waiting to put the message into the queue. Now, when will a particular process or any process which wants to send a message would wait on the message queue only when the number of messages that it can hold, they are all filled already with some messages. In that case, the process which is coming late or coming after the message queue is full, they have to wait. Similarly, when somebody wants to read from the message queue, they can also wait. When will they wait? When the message queue is empty, these processes will be waiting. So there are two queues associated with the message queue itself. Two queues for holding the threads or processes waiting for a message to be delivered or reading for a message from the message queue. That means a message queue is a common entity which has got a handle, okay, which is created once, and it is used by any process who is having the handle with it. So it doesn't matter whether P1 or P2 can wait or P3 can wait. Who has created the message queue doesn't matter. Somebody has created the message queue and the handle is available for each of the processes. They can either send a message to the queue or they can wait for a message from the queue. Now, who is sending it doesn't matter, doesn't know. Maybe you need to design your application such that you will know which process is sending. Otherwise, there is no way of finding out who has sent the message. So, but message will be delivered if somebody is waiting for it. Now, always in FreeRTOS here, it is FIFO order. That means the messages which are coming in are queued up in the FIFO order, first in, first out. But different OSs will support different things. Priority order, based on the priority of the message, it could be changed, and priority of the process which is waiting, it could be changed, but we don't care about it right now. The messages are queued up in the FIFO order and it will be delivered to the process which is waiting for it. Now, one more thing, when we are waiting, the process waiting for either for sending the message or for receiving a message from the queue, they have a timeout also associated with that. We can give, I am willing to wait for so much time. So a process can wait for such a time till a message is received by that process. Then it will come out with a timeout error. Similarly, a process which wants to send a message, if the message queue is full, it can wait for some timeout. So there is a timeout for both sending as well as receiving. So this is all about message queue. Now, since I said that we have a common memory, okay, where is it? Common memory is there. We can create a message queue and then put the handle here, and it will be a global variable which all the processes can access, so that they can wait on the message queue and they can exchange messages between them. Okay, if you are designing an application for specific purposes, you can do that. Okay, how to communicate, what message to do, you can decide to do that. Now, one more important thing about message queue is the size of the message. Whatever is the size is fixed while creating it. Okay, 10 bytes or 20 bytes or whatever. But you cannot have both, either one of them. Okay, one particular size has to be there. So if it is 20 bytes, it will be all messages will be of type 20 bytes. And then one more thing, when a particular task is sending a message to a queue, the message, suppose it is sending some 20 bytes of data, this is T1 is sending, it will be copied into the message queue. Okay, similarly, when somebody is receiving it, they can copy it from there. So it is not the pointer references which are being shared, it is the actual message which is getting copied and then read back from the message queue. When you are reading the message, it will be read from there. So there will be a copying involved from this sender to the receiver. Two copying will be there. So these are the summary of message queues. Okay, let me see if there are any doubts on this. Nothing. Hopefully it is clear. Now let me just quickly show you the slides. I'm not sure what is happening. Okay. This is a new message which is coming. Okay. A queue is a first order, first out. Queue is used to store data or message that is exchanged among tasks. Data will be copied, not a reference to the queue. So data is copied to the queue. The queue contents can be accessed by multiple tasks if the queue handle is available with the task. I explain. Blocking on queue reads, when you want to read from the block message queue, if there is no message, it will get blocked and you can wait on some particular time, wait for data. You can also block for a particular time. Now, when a particular task is getting blocked, what happens? Suppose there is a message queue and there are no messages. A particular task wants to receive from it and it says that I want to time out for 2 seconds. Now this task will be waiting for 2 seconds. It will be blocked. It will be put in the timer queue also, because it has to be woken up when 2 seconds over, as well as it will be in a blocked state. It will be in a blocked state till the queue is given a message by somebody else. So this task is receive task is waiting. Now some TX task is sending a message, then it will be woken up. So it will be removed from the timer queue also, because it said that I want to wait for 2 seconds maximum, but within 2 seconds if the data comes, it will be removed from the block queue as well as from the timer queue. The entry will be removed because the message has been delivered, and it will become ready state. And if the scheduler decides to schedule it, it will become running. So this message will be delivered to the receive task. Okay, that's why I'm saying block state is there. Blocking on queue writes. If you want to block on queue write, that means if message is already full, the queue is full, nobody is receiving the message from there, because when you are creating the message queue, you are creating it for how many number of messages that it can hold. You are saying how much is of size of messages. It should be of same size, as well as number of messages that can be in the queue. So if it is already full, it will be waiting. Okay, the sender will be waiting. So it can be both. And then there is one provision also on multiple queues a process can wait. Okay, you have to, I am not going to explain this or show you that example, but you can look at the queue.h similar to task.h and look at all the functions which are there, and then you can use it based on your need. So that's all about message queues. Okay, so now let us look at one example before we go to the ring buffer. Okay, so let me, okay, now I am going to show you. If you want to use the queue, you have to say FreeRTOS queue.h. You have to include it, and then I am saying that built-in LED is 2. Number of iterations I have made it as a constant so that we can use it based on how much you want to wait, iterations you want to do. I am giving the parameter to the task, that is okay. Now this is the structure queue handle underscore t. 2 queues are created. Remember, I am not creating it within the function. I am creating it in the global area so that this will be visible to all the functions. They can access it using this particular variable. Okay. So setup. In setup, remember to set it up to a particular value, one of the standard values. Don't change it arbitrarily, because I have seen some of you doing it, and then in serial monitor the value is not coming up. I will show you. You have to choose this and the serial monitor same. Otherwise, you will not see any data coming. So normally keep it in one place, one value. It is better not to change it unless you have a specific reason to do that. Do not print anything before setting it up, because it won't be visible. It will not give any error, but it won't be received. Okay, you have to set the first baud rate and then only send anything to the serial port. Now I am doing which core ID. You know that setup is running on core 1, if you remember. In setup only, whatever resources we want, we can create it. So we are creating 2 queues, both queue create, q1 and q2, number of items and the size of message. I am creating a size of only one integer. So whatever is the size, maybe 4 bytes, only that much is the one message. I can send only one integer to the message queue. And number of items, I think I decided as 10 numbers. So 10 messages can be in the queue. So these are the only 2 parameters to create a queue. Okay. Now, if it is null, that means some error, queue is not created, then better to come out here, delete the task here and come out. Don't do another create task and then wait on the message queue where the queue handle itself is not created. You will get into trouble. So these are all the things which you need to pay attention to when you are working on real-time things. If you are not successful in creating the queue, do not create a code or create a task which is waiting on the queue. Okay, it will give an error because this queue is null or it was not created. One good thing is to put a static here so that it is initialized to 0 in case even if you are not created it. Otherwise, it will be some random value could be there, but it is a global variable, so it will be normally 0. Fine. Now what you have done in the setup, we have created 2 threads, 2 queues. Then we are deleting it because we don't want to go forward if we were not successful in creating it. Then create 2 tasks. Now you know that tasks are getting created. They will be running on core 0. Okay, core 1 is the setup and always default we are not deciding which core it has to run. So default it is created on core 0. Now TS task and then stack size, you know that. Fine, 2 tasks are getting created. And then just to see that our program is alive, board is alive, we are blinking it for every 3 seconds each, on and off. Then task create is entering into it, iterations. We are sending a message, tx item, which is initialized to 101. So we send it to Q1, okay, and then we are receiving it on Q2. Okay, we are sending to Q1 some message and then waiting for another message to come from other task on Q2. And then now what happens on the receive task? TX task is doing sending it on Q1 some message and then waits on Q2. Now RX task, when it gets a chance to run, it is waiting to receive from Q2. Oh, sorry. It is receiving from Q1. Q receive is happening. It is waiting to receive from Q1 and then sends it on Q2. Okay. So they will keep exchanging messages and then they end. I think by now you might have run it also, hopefully. So let me complete it. Oh, I'm not connected it. Any questions, guys? Anybody can come on. Any doubts? So one more suggestion I have. I think some of you may be operating that reset button quite often on the board. See, those buttons are all very fragile ones. It may not be built for longer usages. Many times if you use it, it may get stuck and then your board will become unusable. So to be on the safer side, if you have any issues, just remove the USB plug and then put it back. That is better, safer than resetting it on the board, because that switch is very fragile and you might spoil the switch if you use it more often, and in the long run even the board will become unusable. So do not disturb the board, or even do not remove the the micro USB very often. Put it connected and keep it like this. It is much safer, because while doing it you might spoil the board or disturb the board. It's all fragile. You know that it is only costing 500 rupees. So you can imagine the reliability of the board. So do not do anything, especially on mechanical portion. Don't touch the board very often. At least you can remove the USB plug and remove it on the laptop side or on the USB bridge, which is safer. Okay. Okay, I think it is very easy to understand, very self-explanatory. It is one fellow is sending it, another guy is sending the 502 and getting received. After 3 iterations, it is ending it. Okay, we are deleting the task. As I told you, we should make sure that you delete it without any before coming out. Otherwise, you will have a problem and exceptions will happen. Okay. Any questions, guys, before we go further? Is it clear? No questions, or you are answering for is it clear or is it for questions? I don't know. Okay. Okay, thank you. So let us now look at another one. Okay. Okay, now let me explain ring buffer. Little different from message queue. This is also for communicating something between two tasks. Okay, some message. Now the message queue has a limitation. What is that? Once you create a message queue, you have to create it for a particular size of the message. Some size, message size is fixed. So if you want to share some different size of messages, you either will be wasting the queue by sending 1 byte. You will be using a message queue for a 10 bytes of message, or you may say that you are not able to send it because the message queue has only some limited number of bytes. Then you have to create another message queue for it. Now what if you want to exchange different sizes of messages, between the processes, what do? You cannot create for every type of message one queue. So ring buffer is one way of doing it. What is ring buffer? Ring buffer is also similar to a message queue that you can, somebody can put some message into it, somebody can read from it. Okay, as long as they have the handle. Okay, fine. Now what you write is not fixed as a particular type number of bytes. It is not fixed. You can put a message which is of variable length. Okay, now what if I am reading it? Will I read only a part of it, or how do I know what is the size of message which is coming in? That is built into it. Okay, let me explain what I mean by that. Suppose I have a ring buffer, I created it. I am sending 2 byte data. After that, maybe 6 bytes of data. Now each data size is somehow is captured. Then when I receive a message, I will receive 2 bytes of data first time. Second time I will be given 6 bytes of data. So that is handled somewhere, somehow. Now one more thing here is, what is being sent in the ring buffer is not a actual data within that. It is the references. Okay, it is different from message queue. Message queue, actual message is passed. Here references are sent. That's why if I send a 2 bytes of data, I get a reference which has got maybe some length, how much of length of bytes, and then 2 bytes of data. If another message is here, another reference is there which is pointing to something which says 6 bytes of data is there and 6 bytes of data. So that is captured here like a malloc. It is the references which is coming, and then the receiving guy may read from it and then can understand what is the length of message coming. Okay, now what is the size? Now what is the size? I said that the message can be of different sizes. So the total size of ring buffer that you create is fixed on creation. So how much of size? Maybe total size is fixed. Within the total size, I can put it whatever I want. Okay, different sizes of messages, as long as the size is within that and I'm consuming it in the same speed, then no problem. Now one more thing, remember, because references are passed, you do not have the control on how to release them, how to release the memory which is being consumed. So in message queue, what happens is, once you read a message, it will be known to the message queue that that is freed up, that message is, that space is freed up, so one more message of the same size can be put into the queue. Whereas here you have to pass back the reference to the ring buffer to say that I have consumed it. Now you may wonder, why is this condition? Okay, let me explain it. Suppose there is a ring buffer, sender TX has put some data. How does he put it? It puts a reference here, and then the reference is pointing at the actual data which has been there. Now imagine a receiver task has received it. Remember, it has received the references only. Okay, and it may be processing it still. This data is getting processed by the receive task. So the message ring buffer cannot assume that once the receiver has read the reference, it means that the data is consumed, I can release it. No, because it is only past the pointer. So pointer, the task may take some time to receive it, process it. It is not copying from the like a message queue. Message queue, it will be copied into the local buffer, and then message queue can release it immediately. Whereas here references are passed, so they have to wait. Now how does the ring buffer know the reference which has been consumed by the receiver can be freed up or not? So the receiver, the task, has to say, inform the ring buffer that this reference what you gave me, I have taken care of copying it or processing it. Now I am releasing it. So you have to call another function on the ring buffer with the reference saying that I have consumed it. So it is similar to malloc. Malloc is getting the data, you are getting the data from here, and then you are saying free, then it is freed by the dynamic memory allocator. Similarly, this message ring buffer also releases that message only on getting the confirmation from the receiver. Now, one more thing is there. Since I said that variable length of message can be put, there is a problem. Suppose this is the length of the total message which is there in the ring buffer. Now in a memory, imagine that I have some free buffer here and then some free buffer here. Say this is some 4 bytes of free buffer and this is some 6 bytes of free buffer. 6 bytes. Now somebody wants to send 10 bytes of data. Actually, the 10 bytes of data can be split into two, 4 byte here and 6 bytes here. Still the ring buffer can accommodate it. But remember, I said that reference is there, so it will be two references have to be processed and then it is not in a contiguous space. So there are something which is different from normally putting it in a contiguous space in the ring buffer. So when you create a ring buffer, you have an option of saying whether I want this kind of a split of messages or not. If you do not want a split, then in this case, if you have created a ring buffer with a no split option, then if I am trying to put a 10 bytes here, it will say error, give back error saying that there is no sufficient space. 10 bytes of contiguous space should be available for this message to be put. Otherwise, you may have to wait till the ring buffer is available with the size you want. Or you can decide to have a ring buffer created with the split option. That means I can provide the data in two different split and the receiver needs to take care of it on the receiving side. Okay, I am not going to detail because you are not using it, going to use it. Maybe if you want to use it, you may have to read up the documentation and then understand it. Okay, in this example, what I gave you is only a no split option and we are exchanging some buffer messages. Okay, so let me just show this whatever I have written. Okay, before that I thought of explaining you SMP. You might have heard about SMP, symmetric multiprocessing. Our ESP32 is a SMP processor because there are two cores like what I shown. They share one common memory. Okay. Now there are something which you need to remember when you are running a OS on this. Because FreeRTOS is some OS which is RTOS code is there. On top of it, you are having applications running. Application tasks are running. Now, application task 1 and 2 could be running on core 0 or it could be run on core 1. Now, imagine a situation where an application task is calling a create message queue. Create message queue. Now, this create message queue is a function which is part of FreeRTOS. So, that code has to be executed on core 0 now. So FreeRTOS code will run on core 0 when a application running on core 0 is calling a system call which happens to be a FreeRTOS call. Now similar time at the same time, maybe application 2 running on core 1 could also call create message queue. Okay, there is no problem. I can create message queue from both. Now what happens is two processes are running in parallel on two different cores and they call the same message queue function, create message queue function, which belongs to FreeRTOS from two different cores. That means when the FreeRTOS code is ported onto this ESP32, they need to take care of few things because it was originally designed for a single core processor. Now create message queue is going to be called by two different cores simultaneously. Core 0 also may call it, core 1 also may call it. This function has to be reentrant. That means I can call from two different tasks. Two different tasks in parallel because core 0 and core 1 are running in parallel. They don't have to wait for each other's execution and there is no dependency. As long as there are no dependency, they can just execute on individual cores parallelly. That is what is called symmetric multiprocessing, wherein two different processors, more than one, are running in parallel and they are executing a OS also from each of them. That means this FreeRTOS code, the code of FreeRTOS can run freely on both of them. Okay. In some processors, some different operating systems, you may say that any OS related code has to be run on a particular core. Okay, it cannot be run on any other core. But you can also design such a way that the code of the OS can also run from different cores, okay, simultaneously. But you need to take care of some critical sections. Suppose this create message queue is finally going to use some data structures which are belonging to OS data. If two different threads are running this, it may get disturbed. Okay, you need to provide some semaphore. That who is taking care? The OS is taking care of having internally some semaphores or some way of lock mechanism, so that only one thread will use the critical section at the same time. But the function call could be reentrant, but some part of that may be protected, that multiple cores do not execute it simultaneously because it might spoil the OS data structure. So remember that SMP processor is nothing but a MIMD processor. You might have, I have shared, I think, Flint's taxonomy. Flint's taxonomy talks about SIMD, SISD, MIMD, MISD. Okay, this MIMD is multiple instruction, multiple data, because this also executing instructions, this also processing some data. Similarly, this also executing some instruction and it is processing some data. So multiple instructions, multiple data is what this particular symmetric multiprocessing system is. It belongs to that category. If they use a shared memory, they are called SMP, symmetric multiprocessing. So each of these cores are seeing the same memory area and they have a same OS running on that. That means OS code can either run from here or this, or one more processor is there, it can also run from there. So they see the same address space and they can run on multiple cores. So a MIMD type of multiprocessing which has a shared memory between the cores is called SMP, symmetric multiprocessing, which is of category MIMD, but it also has a shared memory, then it will be called as SMP. Now kernel can execute on any processor. As I mentioned, create message queue, I can call it from anywhere. Each processor does self-scheduling. Okay. Now what happens is, suppose you have a process here running and it gets blocked. Then it needs to schedule another process here. So scheduler will be called for this processor. Similarly, this core also can execute a process and then it can get blocked and scheduler will be called. So scheduler can be called from either here or here. And when it is called, it looks at the common pool of ready processes which are there in the ready queue, and then it picks up one of the process and then it schedules them to run on them. But you may have some tasks which are pinned to particular core, pinned to a core 0. Another set of tasks which are pinned to core 1. In that case, only this can run on core 1 when it is available. These tasks can only run on when it is available, whereas ready tasks which are free to run on any core, they can run on both of them. So what happens is, each thread running on each core, when they get blocked or some timeout happens or it gets deleted, the scheduler is called and the scheduler picks up one of them to run on that particular core. If it doesn't have any process to run on a particular core, what happens? Suppose you don't have any process to run, then there is already a task which is called idle task for core 1, idle task for core 0. So when there are no schedulable tasks for a particular core, you cannot keep the core shut down because there is no option here. Otherwise you can shut down the core, but it has to keep running. So it will run an idle task which is meant for core 0. There is one task already created by the OS. It could be run. That will be the lowest priority task which is running on the process, on the core. Similarly, if there are no other process to run, this will be picking up the idle task 1 to run on the core. Okay. I hope this is clear. I am teaching some OS things. I hope most of you know maybe. So each processor does self-scheduling. Okay, each processor does a self-scheduling from the pool of available processes or threads. Part of the kernel can execute in parallel. I said part of the kernel can execute in parallel on different processes if they are not accessing the same part or critical sections of the kernel, which are protected by semaphores. I told you that needs to be locked or semaphores have to be used. Memory management needs to be coordinated. Now suppose you are MLOC, similar to MLOC, there is some function calls are there in this FreeRTOS. So it needs to be protected. Okay, some message which is some memory allotted for some task running on core 0 cannot be used by core 1. So they need to be protected. Okay, there are lots of things need to be taken care of when this multiple cores come into play. This is more complex than multi-programming. Multi-programming of means there is one core, okay, one single core, multiple processes run on that. That is called multi-programming. Here this is called multi-core, which is more complex than the multi-programming. Okay, now let me just quickly complete this. What they have done is they have picked up one version of FreeRTOS, okay, who this guys that Express IF, and then they have ported it onto this processor extensor port, and they have added this SMP compatibility because it has to be run on multiple cores, core 0 and core 1. So they have modified the FreeRTOS code because it is an open source, and then adapted it for ESP. Okay, that's why you cannot just like that run any FreeRTOS on this ESP because it should be ported by somebody. It could be a very good project if you want to take up a FreeRTOS and do yourself the porting of this to a processor, which is very much involved. Okay, you need to know assembly also if you want to port a OS onto a different processor, which is a very difficult task. Okay. Okay, our various features of FreeRTOS have been added. Okay, they have added some new features also. One of them is the ring buffer, which I explained is not available on FreeRTOS. It is only available on FreeRTOS, which is ported to ESP32. Okay, ring buffer. Whatever I explained to you is not there on FreeRTOS. It is only specific to FreeRTOS ported onto ESP32. And then there are hooks, which I will not cover now. It will be too much. There are some tick hooks and idle hooks, which maybe if time permits, I will explain you. Okay, this is another thing which is not going to be covered at all. Okay, that's all about today's lecture. I am not going to talk anymore. Let me see, unless you have some questions, I am not going to talk anymore. Okay. Can blank cells of ring buffer cause garbage value? Okay. I didn't get the question clearly. Okay. What do you mean by that? I'm not able to understand your question. So let me try to explain. What you may be saying is, suppose you have access unused cell. Okay. Unused cell means, suppose, okay, let me assume that there are 100 bytes of ring buffer you have created. This is the unused space. Maybe at the end, then 5 bytes are there. Okay. And then suppose this is freed. Suppose this some 100, okay, 50 bytes are freed now. So, okay, I understand what you are saying. Suppose earlier there somebody sent a message of 5 bytes to some task, okay, RS task, and that fellow took the data, okay, he did not commit back to the ring buffer saying that I have freed up the 5 bytes. If that is the case, it is like a garbage. That means this hole will be there, okay, wherever it is, it will be there. It is similar to MLOC, wherein if you are not freed up, that is wasted. It, as long as the ring buffer is concerned, it is being not consumed yet. Sorry, not freed up yet. So it is being occupied. So it is similar to your garbage value. But what if you are not means unused means, suppose there are some data here which is not freed up, and then you are having only some free data here. You are able to put some data here and then free it up. This will be 5 bytes is very small for any message, then it will be unused. Even that also cannot be helped. It is similar to malloc. Okay, some bytes can be unused. Okay, they can remove if you are not freeing it up properly, then it may become unused. Okay, so let me quickly show you ring buffer. It's very simple. I am sending two data. You can put your name there. Don't put my name. I am sending two different values. One is I'm sending a character, string of a character of some string of characters, and then one integer also. So what I have done, let me explain by one. Ring handle I have created it in the beginning. Then I have some buffer, a string, which is to be sent across that ring buffer, and then I am creating a ring buffer here of size 1024 and no split. I don't want this to be split now. That means I want contiguous space. You can imagine why I am saying no split here, because I am sending a string information here. So if it is split across the boundaries, I will not be able to print it, because all of them, including the null, should be in the contiguous space for the string to be consumed by the other fellow. So it cannot be split. So that is why I have put a no split option here. And then I am creating 1024 so that I can keep sending data between two processes. It is similar to message queue that I can exchange between any processes. It doesn't matter which core it is running from. So I created two tasks, and then TS task is sending buffer send. It sends on integer item. Okay, TX item is some integer which is there. So it is sending on integer followed by some string. I am adding +1 here because string length of my name will not include the null character. But if I don't copy a null, let me explain why I have put +1 here. Okay, sometimes it may work, sometimes it may not work. Okay, let me explain. Suppose if you are sending a ring buffer is there. Ring buffer, I said it's a reference. So some reference, it is allocating some memory based on your string length. Suppose I have put Mauli Sankaran. Its string length is only some whatever, maybe 4 plus 6, 8, 12, some 14 characters suppose. If I did only 14, it would have allocated 14 bytes only. It wouldn't have included the null, because string length always gives you excluding the null character. So what happens is, if I am trying to print from here, I will have problem because it will be not be terminated with a null. So I have to put +1, and I need to take care that the last byte is also null. So how am I taking care of it? I think I am taking care of it by where is my ring buffer? Okay, I have declared a global array, and then I think it will be null will be there in this array. I have to see. Okay, who I am taking care. String length +1, my name. How it is 0? I think it is. I need to check up. Okay, I forgot what I had in mind. How it is +1 is working. Let me see. Okay, so my name +1 you have to do because you have a null character there. I think normally what happens, okay, how is it working? I will tell you. Whenever it is allocating the buffer, where is it? Okay, ring buffer, whenever it is allocating this buffer, it is doing a calloc. Okay, similar to calloc. So it has filled it with all zeros, and then the data is copied into it. Okay, my Mauli Sankaran is copied. So the end character is filled with a null. Okay, that is the reason why it is working without any problem, even though I am not doing it anything specifically. Okay, so I am passing that string, and I am waiting for 2 seconds. Receive task is iteration ring buffer. It is receiving it. It is receiving the same order. First it is receiving the integer, and then the next item size is, it is receiving whatever is the string length of my name. Okay, I am receiving it. Okay, the size only I have declared here. String length of my name +1. So I am only giving the size, and then you have to say, give a address of that variable, and then what you do, you don't need to allocate a buffer because you are getting the reference there. So this pointer, whatever you receive from there, is actually pointing at the name of the name that I have passed. So I am converting it into voids. Sorry, here I am just passing it. Okay, because I have already made it into a character star. Here I am getting a void star. I am typecasting it to character star and integer star. I'm sure you will be able to understand it. So I am printing this values, and then I'm informing the buffer that I have consumed it. So I need to do this so that it gets freed up. So I'm passing the same pointer back so that it gets freed. So I am passing two values and then getting it released. Okay, so let me just run it. I'm sure you might have run it and it is working fine on your side. Oh, okay. Something is happening. Okay, any questions, guys, before it starts running? I think you are also maybe having this problem so often. Don't worry, you'll keep. So I am 3 times I am printing it, name, and then exiting it. Okay, that's all. Now I am going to, no questions so far. We'll explain it and see. Okay, fine. Now I am going to give you one exercise now. Okay, I have almost 1 hour. We have ring buffer I have done. Now interprocessor call. Okay, let me explain what I mean by that. This is little involved. I want to give you an exercise here. See here, you have core 0 and then core 1. Okay, you can actually run some process here, T1, and then you have a function. Let me call this as a function 0. Okay, something you have defined. And then you have a function 1, some which is receiving some parameter, and you have defined two functions called function 0 and function 1. Now you want this function 0 to be executed on a core 0. Okay, you want to say that I want this function to be executed on core 0. Similarly, I want this function 1 which I have written should be executed on core 1. I might call, or I might say that do this on any core from anywhere. Okay, I might call from, suppose I want function 0 to run on this, but who can initiate it? Anybody can initiate it. Anybody can say any process. It could be running here or it could be running here. Tell the OS that I want this function to be executed on a particular core and then come out. Now let me explain. I am, suppose this is a process which is T1 is running on core 0. Okay, after coming somewhere, I am saying that now I want this. It is a T1 is running on core 0. Okay, let me write it as T0 so that it is confusion is less. T0 is running on core 0. Some other task T1 is running on here. T0 wants to run F1 function 1 on core 1. Okay, now it has two options. It has got two options to say blocking or non-blocking. What I mean by blocking, let me explain. That means this T0 is informing FreeRTOS, I want this function F1 1 should be executed on T1. Now that function could take some time, right, to execute. After the execution, it is not going to return, okay, it is a void, okay, it cannot be returning from there, but I want to be informed that this function has been run or not. How can I say that? If I say I am blocking call, if I do, I will be blocked, T0 will be blocked till this F11 gets run on the core 1 and gets completed, then it will be informed back, and then this guy can come out and then start with his job. Or I can say that I am not bothered about blocking. I just say, please make sure that this function is run on the core 1. I don't care whether it is, when it is run, whether it is completed or not. In that case, I can call a non-blocking call of this function. Okay, some IPC call is there, okay, system call. It is called interprocessor, not interprocess. Interprocessor call. That means I am saying I am interested in running a function on a particular core. Similarly, this T1 can say, I want to run this F10 on this core and then inform me back. If I called a blocking call, I will be informed back. Then I will be blocked till this function 0 is executed on the core 0, and then I will continue with that. Okay, now this is what I want. Now, how is it implemented? Let me explain that little bit. Just for your information, it is already there in the reference what I have given you. Okay, what these guys have done is they are running one task here, which is waiting for such functions to be invoked by different fellows. Some IPC function is a process. This is running already, waiting for somebody to call. Now core 0 has some IPC 0 process, and IPC 1 process is running on core 1. Okay, running means it is already created, but it is blocked, it is waiting. So if somebody says function 0 to be executed, some process has to take ownership of running this function. That will be this process. Okay, you cannot execute this function on some other process context. So F10 has to be run, then it will be run in this context. That means this process which is already in block state will be woken up and it will execute this function 0, and if the other guy has called a blocking call, it will be informed back so that it can be woken up, and then it will come again and sleep here. Similarly, if somebody is calling F11 function, which is to be called run on core 1, this task will be woken up and it will execute this function and it will inform back, and then it will get blocked. So this is how it is implemented. I'm not going into the details of it. I hope you can understand it. It needs some OS fundamental. I'm sure you have that to have a clear idea. Okay, you can ask me in case if I'm not very clear. So let me explain it. Due to the dual core nature of ESP32, there are instances where a certain function must be run in a context of a particular core. Okay, it has to be run in a particular core, a function. Maybe allocating an ISR to an interrupt source of a particular core. You want to run that ISR only in that core. So you can do it by interprocessor call. It is another function call. You can use it. A given function can be executed on a particular core by calling ESP IPC call, ESP IPC call blocking. So you will be passing a function pointer. So this function will be called, either it will be blocked or it will be unblocked. It won't be blocked. It depends on where are you calling from. Okay, this function itself may be called from the same core or different core. So there is some mechanism to differentiate it. Now I want you to read the reference. Okay, I explained you how it is implemented. I want you to do this experiment A. What is experiment A? Let me explain. You need to define two functions, okay, which is returning void and then receives a void star, run on core 0 and run on core 1. Okay, both the above functions print the parameter passed to it and then also prints which core it is running. Okay, you know the function to call to find out which core this function is called so that you can verify it. And then you are aware that setup is run on core 1 by default. So in setup, after initialization of serial port, invoke a function called run on core 0. So what are you doing? You are core 1 is here, core 0 is here, setup is running here, and then on setup, after serial port is initialized, you are saying core run on core 0 you are calling. That means what? This function is going to be run on this. Okay, this function is going to be run on this core, because you know that setup is running here. So on core 0 will be run. I am calling a blocked call. Okay, so it will be completed and then it will come back here. Okay, so that is what you are supposed to do. And then setup, create a task. In setup, after that you create a task called core 0 task. That means you are creating a task from here which is going to be run on this. This task is going to run on this core 0, and then it is going to call a function 1 core, this function. Okay, run on core 1. So that will be run on this core 1. Okay, so I want you to do this. Then get into a loop, blink LED for 1 second. Okay, and then what happens is main loop is only blinking. Core 0 task will take control of now. It will be 3 times, it will be in a while loop or for loop, whatever, or you can make it configurable like what I did. Then it will multiple times, iteration time, it will run this core 1 function so that it is run on the core 1. Okay, you know that this task is running on core 0. It is trying to call the function which is running on core 1. 3 times it will call and then it will get deleted. That's all. So I want you to implement this function. If you have any doubt, you can ask me. I will just show the output of the function so that you know what to expect. IPC. Okay. Okay. Okay, now okay, let me explain you what is happening. Okay, see here, loop is running on core 1, entered run on core 1. Okay, before itself core 0 is already run. So enter this function is actually called by the task 0, core 0 task. Okay, this function is executed and it has been passed ABCD and it is running on core 1, it says, and then I am exiting this on core 1, that function, and then it is looping. Loop is running every 2 seconds, and then again it is called, thrice it is called, and then it is getting deleted. The task which is created on core 0 is deleted. So it calls this function run on core 1 3 times and then it dies. That's all. So this is what is expected of you.